Members of the conference, good morning, good afternoon, or good evening to wherever you are. I'm Yanru Chen, an undergraduate student from Jilin University, China, and I have been working on this research with Lawson House Research Institute and Western University. I consider it a great honor to be asked to speak about this novel texture analysis method at EMBC 2020 conference. My presentation will be given in 4 parts. Well, let's start by looking at the introduction. Computed tomography of blood flow in the cardiac ventricles is an established imaging diagnostic technique. Our clinical research provides strong indications that CT imaging of blood flow may permit quantification of myocardial blood flow heterogeneity. We use mechanistic mathematical modeling to gain further insights into our clinical observations. We propose fractal dimension as a clinically feasible index that can quantify the intracardiac blood flow heterogeneity. However, clinical cardiac CT may be currently unable to provide blood flow imaging of the whole heart. The preliminary data presented in this presentation is part of an imaging modeling study designed to fill the gap. Now, let's move on to methodology. CT imaging data from the previous study was obtained and was reprocessed in this work. The cardiac walls were manually segmented using Fiji ImageJ to reconstruct the 3D representation of the patient's specific heart under each of the 4 clinical conditions. The method assumes that coronary blood flow is primarily regulated by the status of the underlying fractal coronary arterial capillary vasculature. It uses the 3D map's probability distribution function and the relative dispersion of the PDF's probability distribution function to compute the fractal dimension heterogeneity index. We hypothesize that multi-thresholding provides further information regarding the underlying vasculature. To test, the 3D map was first thresholded at predefined maximum and minimum values, after which the fractal dimension was computed. Total cardiac blood flow was computed as the summed total blood flow in each 3D voxel. The global fractal dimension was computed as the box dimension of the complete 3D volume. Next slide. Next, I'd like to take a look at results. As you can see from the figure, the right figure, it shows the fractal dimension at various blood flow threshold values. Computing fractal dimension upon thresholding is shown for one data set in this figure. And the left one is how we compute fractal dimension using the relative dispersion of blood flow over n voxels. Dialysis as well as treatment were found to alter fractal dimension as discussed previously. Vasodilation increased fractal dimension and mild cooling promoted reduction of fractal dimension. It was found that thresholding maximum blood flow values in each voxel augmented the contrast between fractal dimension estimates. In conclusion, this preliminary study provides an open-source texture analysis method that brings the clinical and mathematical approaches together. It permits clinical data interpretation in a biophysical modeling context, thus providing further insights into the vasculature status based on the clinical observation. I hope I have shown you a clear picture of this fractal dimension-based texture analysis method. This new method will permit rapid semi-automatic computation of an interpretable texture measure in clinical CT perfusion imaging. You all have been very attentive audiences. Thank you. This is Yanru Chen. I come from China, Jilin University, and thank you all for listening. Thank you all the people from Lawson House Research Institute and Western University.